Hello, I'm Rob Reiner from Tachyum, and today we're going to showcase our latest milestone by demonstrating Tachyum's software distribution package running on our Prodigy Universal Processor emulator. Our software distribution package combines key advancements to deliver optimal performance for Prodigy. Notable updates to Release Candidate 1 include the inclusion of GCC 14.2, Linux 6.12, LLVM 19, FreeBSD 14.1, and QEMU 9.11. The package also provides users with an optimization guide and performance tuning tools to ensure maximum efficiency. We're able to boot Linux and FreeBSD from a partitioned drive using UEFI firmware. We can boot these OSs with various settings such as kernels, kernel parameters, and/or boot parameters. This allows us to craft images for more specific usage scenarios as well as show all the capabilities of Tachyum's Prodigy Universal Processor. Our image is partitioned into several partitions, allowing us to distribute various content such as operating systems, data partitions, packages, or specialized versions of OS root systems for scenarios where more specific build or distribution options are of importance. This image can boot Linux with 4K page Linux kernel, 64K page Linux kernel, or the FreeBSD operating system. We will boot into Linux with 4K pages, which is the standard page size. Later, we will boot into the Linux kernel with 64K pages, which are used for performance gains in HPC systems. Note that the booted operating system is running from the disk partition, so there is no difference in the user space runtime. We're booting into the Linux OS with 4K kernel pages. Here we can see that the kernel we booted has page size of 4K. Here we can see how our image is partitioned. First partition is the EFI boot partition containing the Tachyum boot EFI stub as well as the kernel image for 4K and 64K kernels and the grub configuration file. The second partition contains the Linux root file system with the operating system which we will use in this demo. The third partition contains all installable packages with package metadata to be used from the Linux operating system partition for installation of optional software packages. The fourth partition contains the FreeBSD operating system distribution for Tachyum. We're going to build a bash shell using GCC and later Clang to show real-world package building. Bash is the default shell in various Linux distributions and is an essential part of Linux distributions. We chose Bash because of its widespread use on servers by millions of users every day. We are building Bash through configure, make, and make install commands. We will show the use of GDB debugger on our built shell. We will show how to intercept execution of bash command interpreter and amend misspelled command to show GDB is fully capable of use in the Tachyum OS distribution. We will set breakpoints, inspect data structures, and modify data in a running application. Building software is one thing, but fixing bugs is another. We're able to debug binaries produced with Clang in GDB, setting breakpoints, inspect data in the memory, step through code, and change values in the runtime of the application. Let's set a breakpoint to read command. Let's step through a few lines of code until it asks for commands. Whoops, there is a typo in that command. Can we fix it? This is the command which we typed, but it is already parsed. So we need to alter the global command structure. It should be stored in the simple substructure. Now let's try to fix it character by character. Looks good now. Let's execute it. It looks a bit messy through the debugger but we got the folder listing that we wanted. We will now reboot into the same operating system, but with the kernel configured for 64K pages. The main advantage of using 64K pages is improved performance in memory-intensive workloads, such as HPC and large databases. Here we can see that our current page is 64K. We will show building Bash with Clang, but for that we have to first install the Clang compiler. We showed you the layout of the partitions in the beginning of this video. All installable packages are stored on the third partition, and our OS installation is set up to install packages from that partition. The Clang compiler is not installed, so we have to install it first. The Clang compiler is a newer compiler than GCC, benefiting from the LLVM project. It is essential to support newer compilers such as Clang and software distributions, as many projects benefit from the LLVM ecosystem, opening wide opportunities for porting modern software and future-proofing Tachyum's platform software. We are going to build the same Bash application, but this time with Clang. As we can see, the Clang Bash build was successful. We will examine the .comment elf section in our newly built binary, where the compiler typically records the compiler identification for the built binary. We can see that our newly built Bash shell has been built with the Clang compiler, and we will debug it with GDB just like we did with the GCC built Bash. We will debug our newly built Bash binary we built using Clang with GDB again. The built binary, although it has been built with a different compiler, contains all the necessary information to debug and overlay source code to the binary. We will see that the binary contains debug symbols that can be resolved to actual source code, thus enabling debugging in the context of source code from which the binary has been built. We will, as with GDB, step through the code, set breakpoints, and modify data in the memory on a running application. Okay, let's do some hacking again. The flow will be exactly the same as in the previous example. This time, we will just modify the message. After parsing, there are two string tokens. In the second one, we will just change lowercase letter t to capital T. Let it run, and we can see the altered message. So far, we've shown building and debugging binaries. Scripting languages are a must-have in today's IT ecosystem. They are an integral part of development, infrastructure, and operations of IT systems. Python, Perl, and R are first-class languages on the Tachyum platform because we realize they are essential to modern software delivery. Interpreted languages may have limits in the production runtimes, but they often benefit from very advanced delivery mechanisms such as package distributions, tooling, documentation, and are an integral part of software distributions. In other words, they are installed by default almost everywhere, are easy to learn, easy to distribute, have numerous libraries and frameworks that enable short development time. Now we will show a simple example of running a Python web server using a Flask framework in a Python virtual environment. We will install the Flask framework using PIP or Python Package Manager. The server will serve just simple services, but there are no limits for Python running on the Prodigy platform. Now we will create virtual Python environment for Flask, activate that environment, and install Flask packages. Now we will create simple web server, two endpoints, one for root and one returning a JSON based on query string. We will run Flask and keep it running in the background. Let's see what the first endpoint returns and the second one. What an awesome JSON we got here. Now let's try something different. We'll log in again into a clean shell. We'll demonstrate image classification using a pre-trained ResNet model in BF16 precision. The ResNet model is retrained in BF16 using post-training quantization. The BF16 quantized ResNet model performs all activations, loss functions, and reductions by calling the Tachyum BF16 vector instructions. A batch of 10,000 images is processed, and all of them are classified correctly. The amount of software developed for x86 is vast, and chances are that not all of it will be ported to other platforms, especially for legacy or commercial applications. In such cases, virtualization comes to play. On the Prodigy platform, we leverage the QEMU project emulators for user space binaries, QEMU user, as well as QEMU system for operating systems emulators for x86, 64, ARM, ARM64, and RISC-V hardware platforms. The bin FMT mechanism provided by the Linux kernel allows us to hide the foreign binary invocation in a transparent way to the user. Users can run foreign architecture binaries as if they were native applications, integrating them into the Tachyum ecosystem. In this demo, we will be using the SQLite 3 embedded database for its simplicity and versatility. We will show a simple example running an SQLite 3 database x86 64 binary to create and populate embedded database. Then open the same database using SQLite 3 Tachyum build and also from a Python script. We will try to run an x86 build of SQLite database on Tachyum architecture through QEMU emulation. Let's prepare some data to play with. It will be a simple table with 3 columns: name, size, and permissions. It will be populated from a CSV file we have just created. Let's try a few queries. Note this number. We will compare what we will get from a native SQLite build. But before that, let's suspend the app into the background and see what is actually running. Pure magic. The x86 binary behaves like a native one with the help of QEMU. But will the database file be compatible with Tachyum native build of SQLite? Let's find out. The schema looks fine. Data is there. And the sum of all sizes matches what we have seen previously. Let's do one more test. Open the same DB file with Python and do the query. Looks good. Now we're going to boot into the FreeBSD operating system. FreeBSD is a powerful and flexible operating system that is well suited for both servers and advanced users. While it may have a steeper learning curve compared to more user-friendly operating systems, its stability, performance, and rich features make it a great choice for stable and reliable Unix systems. FreeBSD has been ported to Tachyum and can be built with GCC as well as Clang. FreeBSD is developed as a single cohesive operating system, which means that the kernel, userland, and documentation are all maintained together. It is known for its performance, especially in networking and server environments. Its TCP/IP stack is highly optimized, making it a preferred choice for high-performing networking applications. FreeBSD includes advanced networking features out of the box, such as jails, a lightweight virtualization technology, IPFW, a powerful firewall, and support for various network protocols. This makes it an excellent choice for network appliances and servers. FreeBSD has a strong focus on security, with features like mandatory access controls, secure by default configurations, and a robust permissions model. FreeBSD is well known for its optimized networking stack. Let's download a large file and check the I/O utilization. The system is designed with security in mind, making it suitable for sensitive applications. FreeBSD is known for its stability and reliability, making it a popular choice for production servers. The release cycle is designed to ensure that users receive well-tested and stable updates. We'll start TCP dump to see the networking traffic while downloading the large file mentioned above. FreeBSD's jail system allows for the creation of isolated environments for running applications, providing a lightweight alternative to full virtualization. That concludes our demo. Thank you, and be sure to stay tuned for future Prodigy updates and milestones.